Word. I'm gonna. Oh, I don't even know if my keynote came back. It did. Okay. So I'm going to share the screen. All right. This is where we were. Yeah.
It's not there yet.
Oh yeah. I should also mirror it. Oh, but first, the spinning ball of death. Okay. So you had examples. The word examples or no?
No.
What's the last thing?
I have the word examples.
And what's the last thing you have?
Photosynthesis.
Okay, it goes from radiant energy to chemical energy. Do you have that?
No.
Okay, radiant energy to chemical energy. Yeah, because I got the spinning ball of death, so I'll just narrate it. Kate can see it, and it is being recorded, hopefully.
And then light bulb.
Light bulb, yeah, is electrical energy to radiant energy. If you're looking for a short version of energy, NRG, that's one of my faves. Save yourself some time. Energy to radiant, or yeah, even just electrical to radiant.
Light bulbs, electrical to
radiant. And then engines, and that is chemical to kinetic. And then there's like the next point down is kind of a sub point, so it's indented more, and it says the more efficient the conversion, the less waste. What kind of dog do you have, Nathan?
Giant.
Oh, so maybe you weren't with your dog, because
No,
I think I would have seen. Oh, there you go.
the more efficient.
The conversion, the less waste.
So what's kinetic energy going to?
Kinetic can convert into sound or light or heat. Like if you cannonball into a pool, so that's kinetic energy, and then so it's going to create the splash. People will hear that, so that's sound energy. The waves, so that it's a different kind of kinetic energy, and eventually will kind of dissipate. Runs into the wall, and there's like it feels like nothing goes. Granted, you can see like things move a little bit. So there's waves in here too, but then those dissipate.
Those stupid flashlights that you have to like wind, is that what that is? Kinetic.
Yeah. Yeah, it's storing it momentarily. Which one are we on here?
Those are so annoying. Scared in the dark.
Well,
you have to like wind it up.
Especially when they I have no idea where I am here. Oh, there. Especially when they're getting old and it only works if you're constantly like, so you see the light going, and then as soon as you stop.
My cousin and I, his parents always rent a cabin out like the woods, and it's on an island, like a little island in the lake. And so we always go behind the cabin and just go look around in the woods there. And we went out at night, we had one of those flashlights. We were walking around, and the handle broke off.
Oh.
And he dropped it, and it fell into into a broken log, but we couldn't see it. And the flashlight had just died.
I'm such not an outdoorsy person.
And the flashlight had just died. So
you're reaching.
Where do we go?
You're reaching so even if I'm just worried about looking for the handle. So if you want to try and fix it, there's like spiders and
we couldn't find it.
Mice and
Do you want to go camping?
Dinosaurs. What? Yeah, but I'm not a great camper.
Yeah, so
I go with people who know what they're doing.
You have to just look through the trees and try and see stars to see
Wow.
you get around the island.
Yeah, I guess when you kind of wander, you're not constantly keeping track of where the cabin is behind you. Yeah, it's good thing is the stars were out. It wasn't a cloudy night or something. What would you do? Probably just start yelling then, I guess.
Yeah, we have this one as well.
Okay.
It's not a very big island, but
Okay. Make a fire. You're already into like survival mode. We could catch a Komodo dragon, skin it, make clothes,
it's not a big island. But
fashion weapons out of their teeth.
I'm a camp leader.
You had airsoft guns, so what could have gone wrong?
In the dark.
You're this bear. Oh, you're like. Dook, dook, dook.
We almost did that once.
Holy.
We saw a bear, but we only saw like a small bit of it because of the trees. So we thought it was like a squirrel or something.
So you thought it was a squirrel?
Because of the trees, we can only see a small
Oh
bit of
my
it. So
word.
we're gonna shoot at it.
I wonder, like a bear, if it even feel an airsoft pellet unless it hits it right in the face or something.
Yeah.
But it'd have to be pretty high powered, wouldn't it? Because like such thick fur and everything. Or I just think a bee ran into it or something.
Pretty fast bee.
Yeah, yeah. I'm thinking of more like when I'm biking and a bee's coming at me. But if a bear's
yeah.
just sitting there, yeah, that is a fast bee.
It's pretty fast and solid bee.
So you will need to be aware, not memorized, but just kind of aware of energy transformations. I think the previous page, I'll put it back one sec, Ada, don't panic. Yeah, on page 236, there's a table that shows transformations. You should be a little bit comfortable with it. Again, you don't have to memorize it, but just have an understanding. The other kind of biggest, importantest point here, total mechanical energy is a combination of gravitational potential and kinetic. This is not an exhaustive list, but this is all that we're worried about right now. So because it can't be created or destroyed, if you have the total mechanical and you have one of these, you can find the other one. And that's what we're going to do when we do practice 1, page 241. You got this? Everybody's done writing? Nope.
I missed the equation.
You got the white and the yellow, but you missed the equation?
Yep.
Okay, just checking. Just making sure I heard you right. We're good, all right. All right, now we're gonna pin this. Then we're gonna make the screen bigger. And then if this thing here, you guys gets in the way, just let me know. I know I'm not paying attention. So this is when I have you guys online, you know, the one or two that come when we do it online. If there's a bunch of people, I don't have it all the way open because it just takes up space from my screen. So I can't always tell who's there or not. All right, moving right along.
Oh, there was a lesson, like a last lesson or something, and I couldn't see parts of the screen because you have,
Oh, because of
you
that.
didn't take your icons off, so all I saw was like Kate's icon. You know what I'm saying?
Oh,
Like,
yeah,
on
I
the
do
video,
know what you're saying. I usually try to move it out of the way. Sorry about that.
when you're trying to take notes.
Yeah, I thought I moved it out of the way, but I guess I didn't. Wait, hang on a second. I thought like you guys see this when you look at the video after, like this thing?
I don't
Cause
know what that is, but I see like all.
Like this.
Whoever's on the video.
Yeah.
Sometimes I can see that.
But not always?
But then sometimes it disappears in the middle, so you have to like pause the video to take the notes.
Weird. Because I thought I was always worried that it takes up space. But then I thought I saw something that told me, oh, it doesn't. So I don't even need to worry about it anymore. But okay, I'll be aware. Sorry about that. Okay, page 241, number 1, practice question. A 0.2 kilogram ball. So mass equals 0.2. Thrown straight up from the edge of a 30-meter tall building. So the displacement, I'll say dB of the building is 30. At initial velocity of 22 meters per second, VI equals 22
Wait, sorry, D what?
of the building. So basically the height of the building.
Oh, were you gonna put that down motion?
A little bit, but not really. It's not component vector style yet.
Oh,
No.
no.
The ball moves up to the maximum height. Okay, so we have the building here. And so somebody throws this ball up, goes to the maximum height, and then comes all the way down and splashes into the concrete. Falls to the ground at the base of the building. Use the law of conservation of energy to answer the following questions, assuming that the reference level for gravitational potential energy is the ground level. All right. So, excuse me, A says, what is the total energy of the ball at the start when it had a velocity of 22? All right. So EM equals EG plus EK. Gravitational potential is MGH. Kinetics 1/2 mv squared, or mv squared over 2. Same deal. So let's plug in what we know. Mass 0.2, gravity 9.8, height of the building where it starts. That's what it's asking, right? What is the total energy of the ball at the start? The height is 30. So this is all the potential energy in the situation. And then this is all the kinetic energy because it's like the moment of release. Like there's a ton of energy, not a ton, there's a lot of energy in that ball. V is what, 22? Squared. What is 22 squared? I feel like I used to know that. 498, 488 something, 496. I'm feeling 496, probably wrong. 484, okay. So 44 times 0.1 equals 48.4. So this is 48.4. And over here, 6 times 9.8, it's 58.8. Plus 48.4, so 107.2, 107.2, which equals 110 joules. This is the total energy in the system. And so this is, if you can get what I'm about to say now, it'll make everything way easier. This is the total energy in the system. At any point along the path of this ball, right here, right at the top, on the way down, most of the way down, right at the bottom, right before it hits the ground, every point in that path, this is the total energy in the system. The amount of kinetic will decrease the whole time. The amount of kinetic will decrease. Not the whole time. Here, let me kind of, no, I'm not going to point to it because Kate can't see it. I need a skinnier thing than my fat finger. So right from here, right at the moment it's launched, 110 joules with sig figs. As it goes up here, the kinetic energy decreases because it's slowing down. So the kinetic energy decreases, but while the kinetic energy decreases, the potential increases because it's getting higher. So when it gets right to the top, it has no kinetic energy. It goes up, 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 pause, and then starts coming down. At the very top, it's all potential. It's all potential. So if you have, I'll do this so Kate can see me. How do I do this? Oh, yeah. So make sure I'm in the screen here. So at the top, it's all potential. Kinetics at 0. As it goes down, the potential drops and the kinetic increases. But so right at here, at whatever point that they equal the same, their total together is the total energy in the system. Any points along here, the total energy in the system doesn't change. But right before it hits, it's all kinetic and no potential. Does that make sense?
But the ratio is changing.
Constantly.
But the total isn't.
Nope. So, and then next year we're going to add elastic potential. So for like springs and rubber bands and stuff. Okay, so that's the answer, is it? Yes. 110 joules. Questions? We're okay with that?
We could use that to determine the height.
Is that what question B is? Yeah. So it says, what is the velocity of the ball at the maximum height and what is the maximum height of the ball? Okay, so for part B, the velocity at the maximum height, so we'll say VF, no, I'll say VM. So the velocity, so the speed of this thing right at the maximum height, it's going to be 0, right? Goes all the way up, pause. So that's going to be 0 joules. But then it also asks, what is the maximum height? We could do that with this information. Initial is 22, acceleration is negative 9.8. We could do all that stuff. We could plug it into the 5 equations, or we look at it this way. EM equals EG plus EK. We know, we'll use this number for now. We know that EM is 107.2. Sounds like a radio station. 107.2 equals MGH plus 0. No velocity, so it's 0. So everything is potential. So we plug in what we know of the potential. Mass is 0.2, gravity is 9.8. We don't know the height, so we solve for that. So 107.2 divided by 0.2 times 9.8, 0.2 times 9.8, 19.6, 1.96, 107.2 divided by 1.96. $55. H equals 55 meters, which means that it's 25, like the building was 30 meters tall, so it's 25 meters above the building. 55 meters from the ground. Cool, cool, cool. Kate, I don't see any chats or hear anything from you, so I assume you're cool in the gang. Make some noise, sister, if you need my attention. C, excuse me, what is the velocity of the ball when it hits the ground? Same idea, so EM equals EG plus EK. Gravitational potential is 0 right now. So it's 107.2 equals 0 plus 1/2 times 0.2 V squared. So we solve for V.
Wait, could you explain that a bit slower?
No. So then what we do now, at this point, like when it's right, so this building goes up and then down,
Mhm.
the point right before it hits the ground, that's usually the way it's worded. It's interesting here, it says something about when it hits. The moment before it hits the ground, there is like the moment, there's no potential energy. It's all kinetic. All the energy from this system is now in motion because it's like, it's a hair's thickness off the ground. If you wanted to calculate that potential, you could, but it would be so small it wouldn't matter.
So the potential gravitational energy
Is 0
is zero.
because it's not, because it's a hair off the ground.
It's pretty much-
Yeah. Okay. And at the top of the path, there's no kinetic. It's all potential.
Mhm.
Because, okay. So
So
here,
the ratio is like the furthest from the bottom to the top.
Yeah.
And then it gets closer and meets somewhere in the
Yep.
middle, and then they pass each other.
Yep. Like if I was to, I just wrote 0, but it would be, the mass is 0.2 times gravity is 9.8 times height, which is 0. Yeah.
Right.
Okay. So this is 107.2 divided by 1/2 of 0.2, so 0.1. So divided by 0.1, so it's 1072, the root of. Just check my math, 107.2 divided by 0.1 equals 1072. And now we're gonna root that bad boy, root 33. So 33 meters per second. Is that for velocity or speed? Velocity. So we got to say down. And that's it. See that in the assignment? Well, you will shortly. There's a roller coaster question. You can almost guarantee there's going to be some version of a roller coaster question because those are the funnest. So you know. But that's it. What's it? It's only 1 to 3 that you have to do. Yeah. Any questions, Kate, before I end this meeting? I don't know if the first one